Alrighty, friends. So the last video that I want to have us watch this week is about the Coriolis effect. And I'm actually a little selfishly making this because I want to have it for some of my other classes too, because it is a bit of a weird, funky concept. And I want to have video of sharing what it is, at least to the best of my ability that I can. So, um, let's get into it. So basically, the Coriolis effect is a made up term, which is kind of funky, right? You're like, if it's made up, then why the heck are you telling me about it? Well, it's one of those sort of like made up forces. It's one that, again, that we can observe, but and we can feel it, we can see it, but it's kind of like the centrifugal force where it's like we make it up, but it does indeed exist. It's kind of like our mathematical way of showing that, hey, this does indeed exist. So you can think of it as more of a made up sort of thing, but it is certainly real and it does have impacts on large scale circulations. So things like hurricanes, oceanic gyres, low and high pressure systems in the atmosphere. And so we're going to start talking about it here in the atmosphere, and it will be brought up in the oceans as well. So yeah, it's this apparent deflection of a moving object on a rotating frame, which means Earth. And so I want you to think about if you've ever been on a merry-go-round. And on a merry-go-round, you're spinning, and pretend that you are sitting across from a friend. And the merry-go-round is actually going to be at rest at first. So you and a friend are throwing a ball back and forth. And as you're throwing this ball, and this slide is meant to be sort of like a way to explain this. So let me see if I can do some drawing on here as well. So we're going to pretend like we're here, right? So here's you and here's your friend. And you are essentially throwing a ball back and forth from each other. But again, the merry-go-round is not spinning yet. So you're just tossing it back and forth, no problem, no issues, right? You're able to throw it in a straight line. It reaches your friend. They throw it back to you in a straight line. You catch it. Let's pretend that we're all really good at throwing and catching balls. No harm, no foul if you're not, if you're like me and don't have very good hand-eye coordination. But now, still imagine that you're throwing a ball across with your friend, but now another friend comes in from behind and starts to rotate your merry-go-round. So starts to give it a little bit of a push. Not so much that it's gonna like make you fall off the merry-go-round, but enough that the moment that you try to throw this ball to your friend, the moment that ball leaves your hand, your friend is now over here from where you initially wanted to throw it, right? So you're still throwing it in a straight line, but now your friend ends up all the way over here, right? And you are moving as well, right? So you end up on the other one side, your friend ends up on another, and the ball seemingly curves in midair, which seems almost like an optical illusion if you were to do this in practice. So what you perceive the ball doing is curving when in fact it is indeed still going in a straight line. And again, this is because we are on a rotating framework of our planet Earth. So this slide continues to go through, it explains these each of these steps, so that's what the letters are meant to be there for. And if we were to give a set of rules to the Coriolis effect, there would basically be 4 of them. So objects in motion in the northern hemisphere are deflected to a right angle in the direction of motion. So if we're looking at this image here, so if my intended path is up, my curve, my actual path is actually to the right in the northern hemisphere. In the southern hemisphere, it's to the left from the direction of motion. So that's a really important point to remember. It's in terms of the direction of motion. And Coriolis is 0 at the equator and maximized at the poles. This is due to the mathematical relation that we use to explain the Coriolis force. And I'll try and input it here. I'm not sure if it'll give me much ability to, but basically the equation that we use is essentially 2v omega sine phi, where omega which is this this image here, that is the angular momentum or angular rotation of Earth, and then that sine of phi, that phi is the latitude. So if you remember what the latitude at the equator is, which is 0, and if you can recall back to maybe geometry or trigonometry, what is the sine of 0? 0, right? And 0 times anything is 0, right? So that can help you with this second bullet point here, or second rule. Our third rule actually can go back to that idea or to that equation as well. That little v that I put after the 2, that's the wind speed in general. And so again, if your wind speed is 0, if your winds are calm or your water movement's calm, whatever you're thinking of, then again, 0 times anything is what? 0, right? So if you're not moving, or if your air parcel's not moving, your water parcel's not moving, then there's no Coriolis force being enacted on you. And then the faster the winds, or the faster the oceanic circulation, the greater the Coriolis can act on you. And then last little rule here is that the Coriolis force only influences the direction of the wind. It does not, or water, it does not allow or does not determine how fast or slow the wind blows. So it doesn't help the movement increase, and it doesn't help the movement decrease. When we're talking about the atmosphere, some of the main drivers to wind speed, kind of, in for all intents and purposes, is pressure gradient. So how different are the pressures between one area and another, and then friction, which is really only applied near the surface. So these are kind of, if I were to ask you a short answer question somewhere, what are the 4 Coriolis force rules? This would be the resource to utilize. On the next slide, I have for you some YouTube links if you want, and you can look these up on your own if you are not in a class that you're taking with me. But don't be discouraged if the Coriolis force is not clicking right away in your mind. It is a very odd thing. It's not super tangible, right? So if it's not like super clicking initially, don't be too concerned. You're not the only one. Honestly, it took me about 3 or 4 different classes that I took to understand what it meant. And for me, once I had to derive the equation, I was like, oh, mathematically, that makes sense. Don't worry, we're not deriving the equation in my classes. That's not the scope of our class. But I encourage you to look into some other resources. Those links that I've provided here are nice visuals of what the Coriolis force is, and just different methods and different ways of explaining what it is, which may or may not be helpful for you. So I explain things how I do, and maybe that's not working for this concept, and that's totally okay. So if that's not, I encourage you to certainly utilize other resources as well. More than one source is always a benefit. Please reach out if you have any questions, comments, and or concerns, and I can attempt to answer them as to the best of my ability. Thanks again so much for watching, and I hope you have a delightful rest of whatever part of day you are in. Thank you.